Hello and welcome back to my video series on statistics. Today we are going to have a look at contrasts in R and how to understand the output of the summary command for linear statistical models. Before we can do that, I'm going to introduce you to a new dataset which is called OrchardSprays. So we're going to look at the OrchardSprays dataset, and this has been collected a while ago already. It's a dataset on pesticide and its effects on pollinators. The study was as follows. So there was basically a cage. Let's say it was 1 by 1 by 1 meter or something like that. And inside this cage, the scientists would release 100 honeybees here and then study how attracted or how repelled they were by application of pesticide. And this pesticide is called lime sulfur, and it's not used nowadays anymore. It was used in the old days as a fungicide, for example. And this lime sulfur was applied to an individual honeycomb in a Latin square design. So basically, the authors just took one of these honeycombs with individual cells here, and each of these cells was filled with a certain concentration of lime sulfur arranged in a Latin square design. A Latin square design is arranged like that. You choose at random your treatments here, B, A, C, D, for example, for the rows, and for the columns you also select those letters that have not been used up to now. So basically it's, for example, like that. You have B, A, C, D, and then you have B, C, D, A maybe. And then it's actually like a puzzle to fill in the other ones here. For example, you could put in a B here, a C here, and then there has to be a D down here, and so on. So you keep on filling that out. And this was done for 8 positions, 8 different rows, and 8 different columns. And each treatment here, A, B, C, D, E, up to H, was then treated with a certain concentration of the pesticide, and the treatment H was the control treatment. Alright, so that's for a very quick introduction to this dataset, and we're going to use R now to understand contrasts. Before we do that, I have to introduce you to what's happening here. So basically we're constructing the following kind of model here. The response variable, let's call it y, is modeled as a function of the treatment. And we know that our treatment has 8 levels. Alright, so now the following is going to happen. For each level of the treatment, we're going to get a summary. So the summary table will look like that. Summary table will have an intercept. And then there will be something like treat B, treat C, and so on. Now what does this all mean? It means basically that in a traditional linear model, if you use the summary command, you're gonna get an intercept term, which is that level of the factor that comes first in the alphabet. And then this term, for example, let's say it's 10 here. This will be compared with all the other ones. For example, you get a 2 here and a -2 there. So this means treatment B is 2 units larger than the intercept, and treatment C is 2 units smaller than the intercept. So the actual mean values here for these treatments are 10, 12, and 8. And that's all there is to understanding contrasts in R. You have to be sure that your treatments are arranged in the order in which you're interested in them. In this case, it's easy because they're numbered and labeled from A to H. And we're going to have a look at an example now, opening R, and use the OrchardSprays dataset. So up here we're going to type, and down here at the bottom we're going to see the results of our code. So there are several things we need to do now. The first thing is actually to load the dataset. So we say data OrchardSprays. Okay, so let's look at the structure of OrchardSprays. Be sure to type with a capital O and a capital S here. So the structure is like that. It's a data frame, 64 observations of 4 variables. And there is decrease, row pos, col pos, and treatment. So what's that all? I'm going to explain it in a second. So the decrease, this is actually the response variable. It is how much sugar solution has been eaten by the bees. So the authors were interested in whether these substances they added to the sugar solution were bad for the bees, so were not consumed by them. So the decrease actually shows how much solution has been eaten by the bees, and the row and column positions are just the positions in the Latin square design, and the treatment is of course whether an active ingredient has been added or not. So if we produce a plot, and that's what we always should do at the beginning, we produce a plot of the decrease as a function of the treatment, and the data equals OrchardSprays. And if we do that, we can clearly see what's happening here. So we know that H is the control. So H is basically where nothing has been added. And they consumed, let's say it's milliliters here, so they consumed about 80 milliliters if no pesticide had been added to these individual cells. And then you can see G, F, E, D, and up to A. You can see that basically in the A treatment, which had the highest concentration of the pesticide, almost nothing was consumed anymore because this pesticide really smells like hell, and the bees just didn't want to eat anything of it anymore. So you can see there's a very clear structure in this dataset, which rarely occurs. If you use your own data, it will rarely happen that you have such a nice pattern in there immediately. Anyway, so this is just for illustrative purposes. So we're expecting the decrease for treatment H to be around 80, and for treatment A it's gonna be around 0. So let's see whether we get there using a linear model. So setting up model 1 as follows. For example, we use LM for a linear model, decrease as a function of treatment, and data equals the OrchardSprays. And let's see what's happening here. If we say summary model 1, we get the following summary. I'm just copying, let's just look at these parts here. So the intercept is treatment A. And we just looked at the graph and we saw that treatment A was about 0 down here. And this is confirmed by our output here. The intercept is 4 plus minus 7, which is not significantly different from 0. There was basically no consumption. Now it gets interesting. So treatment B is the difference in intercepts between treatment A and B, meaning that around 7.6 milliliters were consumed in treatment B, and around 24 were consumed in treatment C, and so it goes on and on. And what you can see here is that the standard errors are always the same except for treatment A. This is the result of matrix multiplications, and this is based on one of the most important assumptions in linear modeling, which is variance homogeneity. So the basic assumption is that the treatments here do not differ in variance. So let's see if that's true or not. Let's use a GLS model instead and test whether there is variance heterogeneity. Model 2 is going to be a GLS model. Decrease as a function of treatment. Data equals OrchardSprays. Okay, so there's nothing wrong with that except for that it couldn't find the function, so we need to load a library first. Library nlme. That's the nlme library, nonlinear mixed effects model library. And we're using the GLS function now in order to be able to test for variance heterogeneity. Okay, let's do that. And let's update this model with a variance function. Model 3 gets update. Model 2 weights equals, and now comes the varIdent function. Form equals tilde1. And then what do we want to have there? We want to have the treatments here, obviously. Form equals tilde1 treatment. Okay. And if we use just the AIC of model 2, model 3, we can see that model 3 has the lower AIC value, indicating that indeed it's a better model. So let me just repeat why we did that. So why did we use the GLS function here? We used it because we wanted to test whether the variance in treatments, so the variance in decrease as a function of treatments, was homogeneous or not. So look at the plot once again. You can see clearly that the H treatment here varies a lot. The values here, the decrease measured, is very variable for treatment H. It's much less variable for treatments A, B, and C. So there seems to be like a function of the concentrations applied in these treatments that lead to a constant increase in spread of these values here. And you're not allowed to do analysis of variance or other linear models if you have this kind of pattern present. So that's why we used this thing. So we used generalized least squares in order to be able to use this thing here, the weights argument. This will say, okay, there's going to be a variance function present, and we model the variance as a function of the treatment. That's basically what's happening back here. So we use a so-called varIdent structure. That's nothing strange about it here, nothing to fear about it. It's just every treatment receives its own variance estimate. And then we use the AIC, which is Akaike's information criterion. Akaike's information criterion, to compare these two models with one another. So let's see what happened in the model 3. If we say summary model 3, the first thing to check is, well, what is it? It's the generalized least squares fit by restricted maximum likelihood, which is important if we compare models with different variance functions. We always want to use restricted maximum likelihood. And it gives us the AIC of the model. It's not so important now. And it gives us the variance function. Now it tells us different standard deviations or different variances per stratum. And the stratum is the treatment here. So here the D treatment is used as a reference, set to 1. And then all the other ones are compared to the D treatment. And you can clearly see that A is the one with the lowest variance. B is somewhere in between here. I think the numbering, the sorting comes from the way the data frame has been set up. Anyway, so you can see that there are different variances for each treatment now. The model accounts for that now. And we now get, this is the most important thing, if we remember from the first model, the standard errors for all these treatments down here, for B, C, D, E, F, and so on, were always the same. But now in this model, the standard errors are different. And in particular, they are much higher for the treatments far back in the alphabet, E, F, G, H, and so on. And this affects, of course, the p-values we get in the end and also the t-values. So it's crucial for us to use models that incorporate variance functions whenever there is variance heterogeneity. So we've learned basically in this session up to now, we've learned two things. First of all, we've learned how to interpret these parameters here. So we know that this is the intercept for treatment A. This is the difference in intercepts between A and B, and so on. So this one down here, what is H? It is actually the difference between treatment A and treatment H. And what we also learned is we can model very strangely behaved data where the variances are not constant. So let's look at the plot once more. We can account for these differences in variance here by using a generalized least squares, a GLS model, like model 2. And if you want to see a comparison between the summaries of both models, so we start with summary model 2, which is the one without a variance function. So coming back to it, you can see the standard errors are always 10.25 for B, C, D, E, F, G. But in model 3, if you browse upwards here, scroll upwards, you see the standard errors are not always that particular value. Okay, so what would you do if you would be interested in different things? Now, these coefficients here show only the differences between treatment A and B, A and C, A and D. Now I'm going to show you quickly one more contrast option that I use very often, which is the successive difference contrasts. Successive difference contrasts. Why are they called contrasts? It's just contrasting different treatment levels with one another. Okay, so the successive difference contrasts, they are part of the MAS library. Library MAS, which stands for Modern Applied Statistics with S and S+, which is a book by Venables and Ripley. And the package is developed by these guys also. Okay, so we use the MAS library and we use the contr.sdif function of that library. Okay, so how are we going to do that? We need to change the options. Options contrast equals C of, and then you say contr.sdif and you fill it in twice. Don't need to care about the details here. So we just use this line of code. So we just use this line of code here in order to set the contrast options differently. Now, we have to rerun our model now. We use model 3 from up here again. Both of them, model 2 and model 3, and give them different names. So model 4, model 5. Where is it? Model 5, okay. Control R. Where is it? Sorry. Library MAS, I didn't load it yet. There you go, okay. Things happen. Okay, so we rerun those models. Let's look at the summary of model 5. And that's going to be the last thing in this video. So let's look at summary of model 5. And let's see what happened here. Wow, we get a massively different parameter summary here. So we get the intercept, which is the overall mean, which is 45. So on average, the bees consumed 45 milliliters. And then we get the differences between A and B, C and B, or let's do it that way. A and B, B and C, C and D, and so on. We get the successive differences between the treatments. And the nice thing with that is that you get full statistical power to test for significance. You don't have to mess around with adjusting p-values because you are still within the allowed number of degrees of freedom that you have in your model. You don't do too many comparisons. And all of these comparisons are orthogonal in the model matrix. So I'm showing you these two options. If you use the standard options, standard contrasts, you get comparisons with a reference level. If you use the successive difference contrasts, you also have a reference level, but this is changing all the time, so you do pairwise comparisons of successive treatment levels, A and B, B and C, C and D. Okay, so for summarizing, let's do it on a paper here. When summarizing quickly what we did so far. So we today looked at the following things. We looked first of all at a new dataset called the OrchardSprays dataset. Second, we looked at LM versus GLS models. And third, we looked at different contrast options. And we looked at the so-called treatment contrasts, that's the default, where you have a reference level. And then we also looked at the successive difference contrasts, which compare A and B, B and C, and so on. And with that, I'm done for today. Thank you for listening to me, and I hope to see you again soon with statistical models with R.